Hello everyone, welcome to this talk titled Sequence-Specific Minimizers via Total Sets. I'm Hongyu Zheng, my co-authors are Carl Kingsford and Guillaume Marseille. We are part of Computational Biology Department in Carnegie Mellon University. So to start, let's define what is a minimizer. Minimizers are methods to perform sequence sketches. Here sketches means representative subset of cameras from a given sequence. The way minimizer works is it has three parameters. First two, W and K, indicates how long the windows are and how long the cameras are. And the third parameter is an ordering between all cameras. The way it works is if given a sequence, it will maintain a sliding window of W plus K minus 1 characters. And then in each of the sliding window, it will choose the smallest camera according to the ordering. Here is an example. The first line being the input sequence. Because W is 5 and K equals 3, every sliding window will have 7 characters. So every line after the first line is one of the sliding windows. Using a lexicographic order, we highlight the selected camera in red for each of these lines. And we collect all the cameras that has been selected, resulting in the following sketch for this sequence, which contains 4 cameras in 5 locations. Minimizers are very popular and they are used in many ways in computational genomics. Most famously, they are kind of an indispensable part for remappers now. You see minimizers in many of the state-of-the-art remappers. It's also very useful in camera counters where you use minimizers to bucket race. It's also a useful component for genome assembly. In fact, sometime today, I don't know if it's before my talk or after my talk, you will hear a talk on minimizer space de Bruijn graphs, which is exactly about this. And then in general, minimizers are just very useful for building sparse data structures. We are particularly interested in measuring the specific density of a minimizer, which is defined given an input string, the proportion of chosen locations over the number of cameras in the sequence. The idea being that with fixed W and K, if I can end up with a sketch with less cameras, it will save me time and space. So here, for example, in this sequence, we have selected 5 cameras out of 11 total. So the specific density would be something like 0.45. However, previous works on building minimizers has focused on a different concept called expected density. The idea is that we want to have a measurement of efficiency for minimizers without reference to an input string. So the expected density is what you get if you calculate the specific density over a very long random string. We go against this rule for 2 reasons. First is that it just plainly doesn't work very well for some of the parameters W and K. Here we show an example where W is 100, so the windows are very long. K is between 15 and 25. In this case, you can look at the plots and realize that a random minimizer, which is kind of trivial to implement, is not doing much worse than what is currently doable using minimizer optimization approaches. And they are both very far away from the lower bound, which we know as a matter of fact that is achievable in sequence-specific case under reasonable assumptions. So there is a lot of optimization space between the current best and the theoretical lower bound. Another reason we are interested in specific density is that it's very useful in many applications. Here is a concrete example for using minimizers, which is seed and extend for remapping. The way this works is I have a reference sequence and I have a read sequence. I apply the same minimizer to both sequences. And then to determine where the read belongs to a reference, I look at the C cameras that appear both in the reference and in the read, and I match the read against the reference where the C location matches up. You can look at this plot and get more details. So one thing I would like to optimize naturally is I want to minimize the number of these matches I need to make. So under certain assumptions, we can write down this formula that the number of matches you will need to do in these remappers is proportional to the size of the reference sketch. So how many camera locations you have in applying the minimizer to a reference times the size of the re-sketch, which is the same thing, just over re-sequence. And both of these terms again under reasonable assumptions are directly related to the specific density. So by optimizing specific density over the reference sequence, we can achieve very significant speed ups for potentially very significant speed ups for remappers. So our objective is to minimize specific density over a given input string by designing the ordering between cameras with fixed W and K. Now we want to make one simplification. Because it's very hard to consider a total ordering over all cameras, there are a lot of cameras and a lot of possible ways you can do it. So usually we reduce the problem to find a subset of cameras that we sometimes call it C camera, sometimes call it priority cameras. They kind of mean the same thing. And we want this set of cameras to have a nice property that if I build something called a compatible minimizer from the C, it will result in good sequence. It will result in good specific density. The way compatible minimizers are built are basically I put all C cameras before all non-C cameras. So our task is to try to find a good set of Cs that would lead to good compatible minimizer. Fortunately, for this problem, we know there is a very simple solution. So the issue with this solution is it needs a very strong strong assumption, which is all cameras in the input sequence are unique. So if this holds, what I can do is I can select every W camera in a reference. Again, here is an example where each box represents a camera. It's not a base, it's a camera. And with W equal 5, I select every 5 camera in the input sequence, resulting in this set of perfect Cs with four cameras. In other words, each window will need to contain at least one C camera and at most one C camera. The beauty of this perfect Cs is that if I build a compatible minimizer from a set of perfect Cs, I get the lowest specific density possible for a minimizer, which is matching the orange dash line you seen several slides ago. So what people has been doing when this assumption is not true is by relaxing the requirement for perfect Cs one way, allowing more than one C to appear in each window. So this results in a concept called universal hitting sets, where the set needs to, suggested by its name, needs to intersect with every possible window of W plus K minus 1 characters. And there are established work that says if you can build a small universal hitting set, you can build good minimizers from that. So we use the phrase compare universal hitting sets here. But what we are trying to do here is to not go down the same route, but rather go the opposite route, which is we relax the condition for a set of perfect Cs the other way, where we allow some windows to have no Cs at all, but each window still need to contain at most one C. We call the resulting concept a polar set. You can imagine it as like every polar camera being a magnet, and the magnets cannot get too close to each other, as you can remember from maybe some of these physics experiments from your primary school. But anyway, the formal definition of a polar set is a set of cameras, which we denote as A, that appear at most once in every window of the reference sequence S. Note that this is only required for this only needs to hold for the reference sequence, not for every possible sequence. So with the definition of polar sets, we now wonder what is the measurement of goodness of a polar set? Because ultimately, what we want to do is we want to build a compatible minimizer from a polar set, and we want the resulting minimizer to have low specific density. The way we measure the goodness, or rather in an abstract way, the size of the polar set is a new concept we call link energy, which we denote as L of S and A, S being the reference sequence, A being a polar set. It's defined as the number of polar camera pairs. They are on a reference sequence. They are exactly 1 window apart. So let's take a look at our example where we have 3 polar cameras. The first 2 are exactly 5 bases apart. So they contribute 1 to the link energy. And the second 2 cameras are more than 5 bases apart. So they contribute nothing to the link energy. And as a result, the link energy of the set we show in the slide has equals 1. So how do we use link energy? We have our main theorem of the paper says that if I have a polar set A on a reference sequence S, these are the same notations, a compatible minimizer compatible with A, that is, slash approximately L of SA less cameras compared to a random minimizer. So if you have a polar set with large link energy, you know that you are getting a good compatible minimizer because you can do much better than a random minimizer. And as you might recall from previous slides, the performance of random minimizer is not that bad. It's even somewhat comparable in the cases we demonstrated, like the current best is not that far away from what you get from a random minimizer. We also want to make 2 quick comments. First being that the specific density we are talking about is defined as the number of selected locations over the number of cameras, or somewhat equivalent to the sequence length. So optimizing the link energy also directly optimizes specific density. The second point we want to make is we use the term approximately. So if you take a look at the paper, there is a more concrete statement, but the idea is that there is some error terms in the statement. The good thing is the error terms is only dependent on the sequence. So whatever polar set you build, the error terms will stay the same. And empirically, over common reference sequences, these error terms are very small, usually less than 1% of the specific density, meaning that the link energy serves as a reliable proxy for measuring how good the resulting compatible minimizer will be. In the paper, there are also some other points. We don't have the time to go through every of them, so I want to quickly mention. The first thing is, if you look at the paper, the definition of polar camera sets is actually different from what we have just described. It would be a set of cameras such that no two cameras appear W over 2 bases within each another, and the link energy is also defined somewhat differently. So this makes the task of building a polar set easier because you have less constraint. And then another thing we do to further relax the constraint is we propose the concept of layer polar sets. And with the layer polar sets, even two cameras they are, say, next to each other in a reference sequence could be selected under certain circumstances if, say, they are on different layers. So this further relaxes our design space and allow us to build more efficient polar sets. And finally, finding the optimal polar sets or finding the optimal layers of polar sets are NP-hard problems we have proof in the paper. So as a result, we build some practical heuristics to compute both single layer and multiple layer polar sets. So now we can look at the results we get after implementing the layer polar set heuristics. We use 7 layers as kind of a hyperparameter. And here the purple line is what we get from our method, and the orange line is the lower bound we have mentioned before. So consistent with our previous observation, with current non-sequence specific methods, you don't get to be much better than a random minimizer. And there is a sequence specific method baseline, which is you just pick every W camera, use that as a priority set, which can beat which is able to beat non-sequence specific methods in certain circumstances, but our methods also consistently outperform almost all of the existing methods in a parameter range we are interested in. So we think this is a very promising development, and we hope to see further developments for this to be used in certain tasks. So with that, I conclude the talk. I would like to thank my group members who has been very helpful during the development of this project, and I would like to acknowledge the funding sources that make this work possible. Thank you, everyone.